I think I'm all set up, ready to go then. Is that correct?
Just a minute. Just a minute while we do
Yeah.
our intro. Just a minute.
Perfect. Got you.
Al Laboratorio Internacional de Partículas Elementales de la Universidad de Guanajuato. Lo fundamos el año 2005 para estudiar las partículas elementales y desarrollar tecnología de detección de radiación, incluyendo rayos cósmicos. Hemos atendido a más de 100 estudiantes de servicio social, 30 estudiantes de licenciatura, 20 estudiantes de maestría y 10 estudiantes de doctorado. Desarrollamos investigación en tecnologías de detección de radiación. Hemos logrado algunas innovaciones que han merecido premios nacionales e internacionales. Colaboramos en experimentos internacionales de primer nivel. Hemos creado el Seminario Lederman, difundido internacionalmente a través de medios digitales. Ha llegado a más de 1 millón de personas, especialmente jóvenes de Latinoamérica, en 6 meses. Contamos con invitados internacionales expertos, líderes en su área, de primera línea, que exploran las fronteras de la ciencia. Hemos publicado más de 22 libros de divulgación y referencia y más de 100 artículos de ciencia en revistas indexadas a nivel internacional. Los esperamos. Bienvenidos al laboratorio. Let me start in Spanish. Saludos y agradecimientos desde la Universidad de Guanajuato, en colaboración con el programa STEAM de la Universidad de San Carlos de Guatemala, con la Embajada de los Estados Unidos en Guatemala, con la Cátedra Eugenio Méndez de Ocurro y la Escuela Superior de Física y Matemáticas del Instituto Politécnico Nacional en México. Gracias a todos ustedes, hemos superado los 1.500.000 participantes desde que iniciamos esta serie de seminarios. En promedio, más de 3.000 participantes por día. Sabemos que nos siguen en este seminario de casi todas las Américas, desde Argentina, Chile, Perú, Colombia, Uruguay, Guatemala, El Salvador, México y otros países. También de España, Alemania, Estados Unidos y otros países y comunidades de habla hispana en todo el mundo. En este seminario tenemos como invitado al profesor Felix Flicker. El profesor Flicker es profesor de la Escuela de Física y Astronomía de la Universidad de Cardiff. El profesor Flicker imparte este seminario titulado MONOPOLES, o en inglés MONOPOLES. Esperamos que sea de mucho provecho para estudiantes de física y para los estudiantes y público en general. Recibiremos sus preguntas por chat. Now, let me say some words in English. Thanks, Professor Flicker, for accepting to speak in this Lederman seminar. You are very welcome, and the public is yours. Thanks.
Well, thank you very much. I should just mention I've actually moved recently to Bristol University. So Cardiff was correct the last time I spoke here, but I'm now at Bristol University. But thank you very much for the introduction and for having me back as well. Yes, thank you. Yeah, yes. So I think I'll share my screen to start with. Let's see how that goes. So I'll share the talk. Here we go. So I hope this works. Let me try. We should have tested this out before I started, probably. But we're going to go full screen. No, we're not. Okay, so we're just going to stick with this. Fine. Okay. Yes, thank you for having me back. And today I'm going to be talking about the topic on this slide here. So in particular, I'm going to tell you about an adventure that has been undertaken fairly recently, in which teams of explorers from around the world have been pulling together to try and find the North Pole. Now, I know what you're thinking. We already found the North Pole back in the early 20th century. Well, these explorers are not searching for the North Pole of the Earth. They're searching for the North Pole of a magnet without the South. And that's what we'd call a magnetic monopole. So let me just, I just want to sort my slides out a tiny bit here because I can see we're not going to get the full screen working, but it always gets these sorts of things. There we go. All right, let's try and get down to the next page. Oh dear. Let's try this. Okay, maybe that'll work. No. All right, well, slides are going to be tricky today. Anyway, here we go. So here's a map of trying to get to this North Pole, and there's an analogy here of adventurers going off and doing things like a sort of discovering the North Pole in the early 20th century. But let me stick with it. So here's the map of where we're going to go exploring, and we're going to start off down here in London. In fact, I'm in Bristol at the moment, and I think most of the people watching are nowhere near here, but I had to get to the North Pole and I'd already made the map. So let's just pretend I'm in London like the last time I gave the talk. And I'm going to start by presenting to you the challenge. So what are magnetic monopoles? What are the things we're seeking, and why are they interesting, and what do we mean by them, and why should you want to listen to the rest of the talk? And once I've presented to you the challenge, what are these things we're going to go looking for, I'm going to present to you the route we're going to take to find these things. And in particular, the route is going to be to search special materials called spin ices. So rather than search the ices of the North, looking for the North Pole of the Earth, we're going to search particular materials called spin ices. I'll explain why they're called that. And we're going to look for this North Pole without the South. Next, I will tell you about the expedition itself. So I was fortunate enough to be involved in some work where we went looking for these magnetic monopoles. So carried out by experimental collaborators of mine. I'll tell you what the experiments were that they did, what the results were, and why we think we have good evidence for these magnetic monopoles. And then rather than return back to England, we're going to shoot off the edge of the map and go in search of new frontiers. And in particular, it's the first time I gave this talk was about 3 years ago now, and there have been some developments since then. So what I'd like to tell you about is some new theoretical work that was published very recently, explaining some of the background to some of the things we didn't understand when I first put this talk together, but I wanted to tell you about today. So there's an update since I first gave this talk. Okay, so if I just try and stop screen sharing. Is that going to work? Perfect, it has. All right, so I should have appeared again. So first, let me tell you about magnetic monopoles. What are they and why are they interesting? And let me just, I'm having real technical difficulties today. I do apologize for that. Good, okay. So magnetic monopoles, the theory of magnetism and indeed the theory of electricity were really the modern theories were started to be developed in the 19th century by this person. Let me share a picture again. Michael Faraday, shown here, giving a lecture at the Royal Institution, where he actually did most of his work in the labs at the Royal Institution. So it sort of sticks with the 19th century explorer theme that I wanted to have for this talk, to show Michael Faraday here. And Faraday worked out what we now understand about magnetism, or much of it. And in particular, here's a drawing of the lines of magnetic flux around a magnet drawn by Faraday. And what you see here is these lines of flux coming out of one pole and going back into the other. So the magnet has two poles, a north and a south. And I think this is as most of us learned in school. And something else we may have done in school, and that Faraday himself did, if we look in another page in his notebook, we see this. So this isn't a drawing. What he did here is he put a magnet under the page, and he put some kind of glue on the page, and then he sprinkled iron filings over the page. It's an experiment you might have done yourself at some point. And so you see that these iron filings are little tiny bits of iron, and they're magnetized. And you drop them on the page, and they orient themselves with the magnetic field lines. And you see that there are two poles here, one on the left and one on the right. And this is the north and the south pole. Now, if you take a magnet, north and south, and you chop it in half and pull the two halves apart, there's one of two things that you might imagine happening. The first thing is that maybe you get the north pole in the left hand and the south pole in your right. You pull it apart and you get the two poles separated. But of course, that's not what actually happens. When you take a magnet and you cut it in half, you pull the halves apart, you get two magnets, and each of them has a north pole and a south pole. So why is this? That's the question. Why is it that you can't separate the north pole from the south? You always get both poles together. So elsewhere, this is all coming from Faraday's journals. He kept very neat journals, and he bound them himself as well, and he had this very neat handwriting. And you can see here an experiment that he carried out in which, and this is really the essence of our modern understanding of electricity and magnetism. And so in this experiment he's describing in words here, he built a coil of wire and he passed a magnet through the coil of wire. And he found that when he did that, the coil of wire gained an electric current through it, and he was able to detect it, for example, like this. So he found that electricity and magnetism, they might seem like different phenomena, but really they're very closely related. And in fact, the modern word we use to describe both is electromagnetism. They're kind of two sides of the same coin. And so in particular, Faraday showed that if you take a magnet and you move it through a coil of wire, it generates an electric current. And similarly, if you put an electric current through that coil, it will generate a magnetic field. So they're kind of related to each other. Now the question is, why can't you pull the north pole off a magnet? And I'm going to come back to this experiment in a second to answer that question. But at a more elementary level, we can say, well, here's the magnet. And we typically paint one end north, one end is north, we paint that red typically. I don't know why, that's just the convention. And the other end, we often paint south. If you've seen a magnet, you've probably seen it colored like this. Okay, so when we chop it in half, why can't we get the north to separate from the south? Well, to answer that, let's zoom in to a smaller scale within the magnet. So we'll define the direction of a magnetic field to be like this, pointing from the red end is north, like that. And when we zoom in, we get something like this. So we find that the magnet itself is made up of individual magnetic domains. So the magnet might be made of something like iron, and then each of these domains, this is still the same iron, but each of these domains has its own magnetic field. And these are pointing in different directions, but on average, they point to give the whole big arrow, the magnetization of the whole magnet. So that's what a magnet looks like when you zoom in. You might zoom in, they could be at most about 1 millimeter in size, maybe about 1/10 of that, or even 100. So they're kind of small things, these domains, and there's many of them in a magnet. So the simplest answer as to why you can't get the north pole without the south is that if you take that big magnet and you chop it in half down the middle, and you separate the two halves, well, each half is still made of domains. You've got a load of domains on this side and a load of domains on this side. You chop down the middle and separate them, but each half is still made of domains, made of little magnets, and their magnetic fields add up to the magnetic field of the whole magnet. So, okay, you could say, yeah, but what happens if I take one of those domains? So each one of these domains has its own little magnetic field, and I try and chop that domain in half. Can I separate the north from the south that way? So when we zoom into an individual domain, we see that one of these individual domains is made up of atoms, and that's what's shown with these little balls here, and each atom has its own little magnetic field. In fact, often these are ions rather than atoms, so that an ion is an atom that is electrically charged, but that isn't too important to the story. The point is that each of these atoms has its own little magnetic field, what we call a spin. It's just the name for the magnetic field of a single atom. And these spins will all align, they all point in the same direction within one of these domains. So the overall magnetic field of a domain is made up of all the little magnetic fields of the atoms within it. And so then you could say, well, let's try and chop a domain in half. Can I get the North Pole off the South that way? But of course you can't, because you chop it in half and it's still made of atoms. Each half is made of atoms, and each atom has its own little magnetic field. And so then you could say, okay, let's try and chop a single atom in half, but of course you can't do that. There's no way to chop an atom. And so then you're stuck. That's why you can't pull the North Pole off a magnet. You can't separate the North from the South. But the thing I wanted to highlight, and so this is our modern theory of how magnets work, but the work really started with Faraday. And when we go back to this experiment I showed you the picture of just here, remember this told us that electricity and magnetism are really kind of deeply linked. And there's a kind of deeper reason why you can't pull the North Pole off a magnet. And that is as follows. So in this picture here, you see, as I said, you move a magnet through a coil of wire and you get an electric current. So if I'm going to stop screen sharing so you can see me. So I'm going to wave my hands around a lot in this talk. So I thought I think you see me bigger when I close the picture down. I hope you do. So let's imagine that this is an individual electron. Okay, so it's an electrically charged particle, has a negative charge. Now, an electric current, like, flows through the coil of wire in Faraday's experiment. An electric current is just a flow of electrons. Okay, so the fact that you could put an electric current in a coil and generate a magnetic field tells us that if you could take a single electron, an elementary particle, just a particle by itself, and you move it in a loop, and I think if I remember it rightly, if I move it so it's moving in a clockwise loop like this, you see a north pole of a magnet, okay? Because remember, if I take the electron and move it in a loop, then that is a little electric current, because electric current is just a flow of electric charge, and an electron has an electric charge. So move it like this, you get a little flow of electric charge, you get a current. And Faraday's experiment showed us that an electric current generates a magnetic field. So if I do this, then I would get a little magnetic field. And in a sense, that's what's happening in the atom. Really, atoms are quantum mechanical objects, and it's a little bit more complicated than this, but the basic idea is you can sort of think of the electrons sort of orbiting around the atom. That's a loose way of imagining what's happening. And so the electron's sort of moving in a little loop like this. Now, if I move it in this direction, you get a north pole because it's moving in a clockwise direction. If I were to turn around, I'm going to try this live on my swiveling chair here. So if I take this same thing, I'm moving it in a clockwise direction as you see it, then this is a north pole. But if I continue moving my hand exactly the same way and I turn, then now, hopefully, you're seeing it move in an anti-clockwise direction. Or rather, no, sorry, you saw it as clockwise before, now you saw it as anti-clockwise. Whichever one you saw first, it looks the opposite when I turn around, but really I'm doing the same thing. You're just looking at it from the other side. So let's see, you want to go clockwise like that, so that would actually look like this. Sorry, I was doing it the wrong way around the whole time, unless my camera flipped me. So if I move it like this from one side, it's going, say, clockwise as you see it, but I do exactly the same thing and I turn around and then it looks like it's moving anti-clockwise. But it's the same motion. So a north pole seen from one side is really a south pole seen from the other. And in that sense, it's kind of philosophically impossible to separate the north and south poles. So that's the answer. That's the setup to this talk. That's the idea of this of what we'd like to do. So we have whenever we have a north pole of a magnet, we always have a south pole along with it, and those are some of the reasons why. It ultimately comes down to the atomic scale, but even smaller than that, you get a magnetic field by moving an electron in a loop, and looked at from the other side, it gives you the other pole. So there is no way to separate the north pole from the south. But of course, I'm going to try to tell you how to do it in this talk. So having explained why you can't possibly do it, let me explain why we think you might be able to do it. So let me share a picture with you quickly. And I should say, I've offered to take questions at the end, I thought, rather than having them in the middle. So if you're confused about anything, please ask at the end about it, and I'm happy to give more information. So the theory of what happens if we could pull the North Pole off a magnet really started with this man, Paul Dirac. And he wrote down the theory in about 1931, I think it was. And Dirac made a number of interesting observations in this paper that he wrote. And I think principal among them is this. He said, well, okay, so the reason we can't get the North Pole off the magnet is because the electron's moving this little loop. But there's something kind of hidden in that story, because the electron has an electric charge, right? And the electric charge is like the equivalent, the electric equivalent of a north pole of a magnet, in the sense that you can have a north pole, but you always have to have the south come along with it. But you can have a negative electric charge without having to have a positive charge come along with it. We have positive charges, of course. We have things like protons have a positive charge, or a positron, also hypothesized by Paul Dirac. And these things have positive charge, but they don't always have to come along with a negative charge. I can just have a negative charge, an electron by itself. And so Dirac observed, well, this is kind of a discrepancy. We have this idea that electricity and magnetism are really two sides of the same coin. This is what Faraday was telling us. And if we wrote down a big list of all the different things in electricity and all the things in magnetism, we'd see that they're in exact correspondence to each other, with one exception. And that is that you can have a negative pole of an electron, but you can't have a north pole of a magnet that would be the equivalent. Okay, you can't just have it isolated. And so the real reason, the deepest reason why you can't pull the north pole off a magnet is that there's no equivalent in terms of the elementary particles of something like an electron for magnetism. And that's what would be called a magnetic monopole. Okay, so an elementary particle like an electron, we could say it's that, in a sense, it's sort of the smallest building blocks from which the world is made up. If you look inside the atom, you find it's made of electrons, protons, and neutrons. And we can call those things elementary particles. You could say there's something, it's something that could exist by itself in the vacuum of space, and it can't be reduced to other things with that property. So an electron just can't be broken up into smaller things. So the real answer is, we can find electric charge in our world. You can take a balloon, for example, you can rub it on your jumper and it'll get an electric charge on it, which you can detect by putting it near your hair and it'll get attracted. And you can't do that with magnetism, and the real reason is because there aren't magnetically charged elementary particles. If there were, they would be called magnetic monopoles. And a monopole means one pole, whereas usually we get the two poles, the north and the south. So then Dirac said, okay, let's imagine that actually there are elementary particles called magnetic monopoles. We've just never detected them. And that's true. We still, to this day, we've looked for them for a long time and we've never found a magnetically charged particle, but they might exist. And he said, let me try and work out what the consequences would be of one of these magnetic monopoles existing. And he derived some rather remarkable properties. And one of the reasons that we think that this is a sensible thing to talk about is one of the things that he realized in this paper in 1931, Paul Dirac. He said, well, actually it would answer a rather deep and perplexing mystery about the nature of the universe, which is about the electron. And it's, why is electric charge, why does it always come in fixed amounts? It's always quantized to fixed quantities. So when you took that balloon and you rubbed it on your jumper and you used it to attract your hair to the jumper, if you measured that's because the balloon gets an electric charge. And if you measure the electric charge on that balloon very precisely, you would find that it always comes in multiples of a very small amount. And that smallest amount is the charge of a single electron. So now, the interesting thing is that the laws of physics, they certainly allow for this. They allow for all electric charge to come in these discrete amounts, these multiples of the electron charge. But there doesn't seem to be anything in the laws of physics telling us that all electrons must have a fixed charge. Why can't it come in like, why can't one electron have slightly more and one have slightly less? Why can't electric charge come in any amount rather than always multiples of the smallest amount? And as far as we can tell, there are no laws that dictate that that must be the case. Nothing would really go wrong in the other laws of physics if we allowed it to vary, if it contained a continuous range of values rather than a discrete set. And what Dirac said, and so we still don't have a theory for this, by the way, why electric charge is quantized. But Dirac observed that if there were even a single magnetic monopole in the universe, then it would be a natural consequence that actually all electric charge would have to be quantized for the world to be as we see it. And he kind of said it sort of half jokingly at the time, but in the almost 90 years since in fact, over 90 years now since the publication of his paper, we haven't really come up with a better explanation as to why electric charge always appears in discrete multiples of this smallest amount. And so this has kind of led to us starting to think, well, maybe he was right. We haven't seen any of these magnetic monopoles, but what if they're really rare? And they might be really rare because they're very heavy as elementary particles, for example. There only needs to be one in the entire observable universe for all electric charge to be quantized. And since electric charge is quantized, perhaps that's why it's happening. Now, that's not the only possible reason, but it's an interesting hypothesis. So There are other reasons to believe in these magnetic monopoles as elementary particles. Some of our fanciest modern theories of physics involve them, in fact require them. So things like string theory, if you've heard of that, requires the existence of magnetic monopoles. So there are lots of reasons we might think that they might exist, but I should say that we've been searching for them for a rather long time now, essentially since the early 1980s, and we've never seen them. Or, well, there was a single experiment where they thought they'd seen one, but it's never been repeated. So it might be that they're very rare, but it might also be that they don't exist. Now, so that would be sort of the end of this talk, if that's where it went. But what I'd like to tell you about today is not an elementary particle. So that all this stuff I've just told you about, these are about elementary particles, and this seminar series is really, I know it's based around the idea of elementary particles, or at least you have a sort of strong background in this. So I'm not going to talk about elementary particles anymore. The stuff I've been talking about, it's theoretical physics, but it's been theoretical particle physics. Now, I'm a theoretical physicist, but I'm not a particle physicist. I'm a condensed matter physicist. And so we don't study the elementary particles by themselves. We study matter, the stuff that gets made of loads and loads of different particles and atoms stuck together. And it's in that context that we believe that we've seen some evidence for the existence of magnetic monopoles. So what I'm going to tell you about is not elementary particles. Okay, it's things that come about as the effective description on a bigger scale inside real materials. So let me move on to talk about that a little bit. Let me just give you a quick update with some slides. So I'm having to switch back and forth like this, but after several years of pandemic, I still haven't got Zoom working properly. All right, here we go. So let's go on the talk. Okay, so I've presented to you the challenge, magnetic monopoles. And what are they? Well, they would be something like this. They would be the north pole of a magnet without the south. And in particular, they would be particles that have a magnetic charge. That is the equivalent of an electric charge, which an electron just has electric field coming out of it, and it's just a pure source of negative electric charge. Whereas a magnetic monopole would be a different elementary particle, and it would be a source of north pole. The north pole would just come out of it in the same way. So that's the challenge, trying to find these things. Let me move on now to the route we're going to take on our expedition in search of the North Pole. And that is going to be to search particular materials called spin ices. Okay, so let me switch back to talking to you again so you can see me. So there's going to be a trick to it, and in fact, it's a very old magic trick that materials use to show these magnetic monopoles. And I'm going to demonstrate this magic trick to you now. It's pretty rudimentary. It's about the only magic trick I can do, and that is to take my thumb here and try and pull one end of it off without causing myself too much damage. So I take hold of the thumb like this, and I twist it, and off it comes like that. There you go. And I can stick it back on, and there it is, back together. Now, I'm sure you've probably seen something like that performed before. Now I'm going to reveal the trick. I'm sorry if that's ruining magic for you, but the trick was that I didn't use the one thumb you thought I had. I had a second thumb hidden over here, and I pretended using my two thumbs to make it look like I had one thumb pulled in half. So by having two thumbs, I can give the illusion of one thumb being broken into two. Now, when this happens inside materials, it's a phenomenon we call fractionalization. We have lots of different copies of something, and it can make it look like a single copy has broken into bits. And we're going to do that with magnetic fields. We're going to take multiple magnets and use them to give the illusion that we have individual magnetic monopoles. So it's like we have multiple things that each have a north and a south pole, but by having lots of them, we can make the north separate from the south. Now, it's a little bit of a trick, but it's also reality. So I'll expand on what I mean by that in a second. So don't go away thinking it's just all a big con. I do believe these things are really worth investigating further, and I'll explain why. So let me show you a little picture here. So here we have a set of, I'm just going to give you the basic idea of how this works. So here's a set of magnets, and you can imagine these are big things. We put them down on the table, pointing north, south in a line. This is how they'd like to line up. Now we can imagine taking one of those magnets and flipping it. So let's flip one there. Sorry, if I can switch slides better, it would look better, almost like an animation, but it's not going to. So we're going to take one of those magnets and flip it. And you see they're all pointing north-south as before, except for one of them, where my mouse is, has flipped. Okay. So, but if we now imagine that we blur our eyes, and we blur our eyes so much that wherever we see a north and a south nearby, it kind of blurs out to nothing in particular. But when there's two souths together or two norths together, we'll see that as a sort of fuzzy region of south or north like this. Okay, so we blurred our eyes and we don't see it when there's norths and souths next to each other. So everywhere else in the big long chain of magnets, we see here's north and a south, here's a north and a south. But now we've got two souths together and two norths together. And this is a little bit like a source and sink of magnetic fields. This is like a magnetic monopole, and it's antiparticle, what we call an anti-monopole. And if we flip the next magnet along in the chain, well, we can move the double south away from the double north, right? So let me just go through that again. So if we have the double south next to the double north, I'm going to flip this magnet, leave everything else the same, and I move the south away from the north. And subsequent flips can move them further apart like this. Have I got one more? Yes, I have. And so you see, by having multiple magnets like this, I can make a concentrated region of north and a concentrated region of south. And I can separate them. They can move around freely along that line. And in fact, you might imagine they'd want to sort of attract towards each other, just like an electron and its antiparticle would do. Okay, so that's the basic idea. I'm going to show you now the same idea, but in 2 dimensions. So 1 dimension is along a line, 2 dimensions is living in a plane, something like this. And so I can take a set of these magnets like that. And if I were to place magnets like this, and I've constrained them so that they have to sit in the places that they're sat, but we'll say they can flip, okay? So they can switch which direction is north and which one's south in each bit. But 4 of them meet at each of these meeting points. Well, the lowest energy state, we know that north and south like to point towards each other, right? You don't like 2 norths together if you try to put magnets together. But the best these can do is to have 2 norths point in and 2 souths point in, so that given the way we've forced them to sit, that's the best they'll do, because then you've got a total amount of no overall north or south in any particular place. But there's lots of ways for them to arrange so they can do 2 norths in and 2 souths in. You can see some different examples here. So the 2 norths might be opposite, say, and the 2 souths opposite. Okay, so this then you might imagine would be the lowest energy setup. But I can reach in and I can flip one of these things, just like before. So that's the one I'm going to flip, and I'll flip it. There it goes, it's flipped now. And just like before, I get a concentrated region of north, where there's 3 norths in now and 1 south. So there's more north than south here. And it must be next to a region of concentrated south. There's 3 souths and the north. And subsequent flips like this can separate the north from the south. Off they go. And so you can think of these things as very much like particles that are moving around. Now, let me explain a little bit more what I mean here, because of course they're not really particles. There's not really anything there. It's just a load of magnets, right? So let me stop my screen share so I can again talk to you a bit more. So this is what we study in condensed matter physics. So in particle physics, they study what are called elementary particles, the basic building blocks from which the universe is built, things like an electron. Now in condensed matter physics, we study particles, but they're not elementary particles. They're what are called emergent quasi-particles. And if you saw my previous talk in this series, I spoke at length about these quasi-particles and the kind of magic that I think they exhibit. But in particular, let me just give a simple explanation of one. So if we take another elementary particle that you may have heard of, if you take light, for example, so light is you can think of it as a wave. But if you give a quantum description of light, you would describe it as made up of particles. And those particles are called photons. Photon is a particle of light, and it's an elementary particle. It can fly through space, and it can't be reduced to other things. It can exist by itself in space, and it can't be reduced to other things with that property. Photon is a photon. Now, you might ask, well, light is a wave, classically, and sound is also a wave. So can you have a particle of sound? Well, you can, in a sense. So you can't have an elementary particle of sound, because my definition, maybe it's a bit loose, but my definition of an elementary particle is something that can exist by itself in the vacuum of space and cannot be reduced to other things with that property. Now, light can travel through space, but sound can't. Right? You can see the sun, but you can't hear the sun. So there can't be an elementary particle of sound, because sound just can't exist in space. But sound can exist in materials. you take a lump of stuff, really, or air, in fact, is surrounding it at all times. But let's imagine taking something like a metal, and you tap one end of the metal, and sound travels through it, and you can hear it at the other end. And if you describe how the sound travels through that metal, and you give it a quantum mechanical description, like you did for light, then indeed you can describe that as being conveyed by particles. And those are particles of sound. And rather than call them photons for light, we call them phonons for sound. Okay, so you can think of sound traveling through a metal, or in fact any crystal, as being carried by particles of sound. And these are what we call these emergent quasi-particles. They're not really there at the most basic level, but I think they're no less real. I mean, sound does travel through a metal. It's exactly the same mathematics that describes it. The same maths that we use to describe the elementary particles, the reason we believe them is what we call quantum field theory. And quantum field theory, that exact same mathematics describes the behavior of particles in materials, and it describes them as things like particles of sound. So I'd say those are the real things. Those are the things you experience in the world. And in that sense, though, these are emergent quasi-particles are real. But in that case, you could say, well, sound's traveling through the material. Of course, really sound is, there's just movements of atoms, and that's conveying the sound as they sort of wobble back and forth. So in a sense, if you look for those particles, they're not really there, but in another sense, they are. They're a collective thing. They're a collective behavior of all the atoms. And I would say they are no less real. In fact, they're the things that we tend to experience. For example, when you detect an elementary particle like an electron, you don't really detect the electron by itself. The electron has to interact with other stuff. And so in that process of interaction, it becomes something slightly different to the elementary particle. It, in fact, becomes a form of emergent quasi-particle in the detector. So there's really sort of only a philosophical distinction between these things. So let's get back to our description. I wanted to say that because I don't want to missell this as thinking we've discovered elementary magnetic monopoles, but I think these things we've discovered in a sense are very similar. So I was showing you how to flip magnets and move these things around, and here's another flip, and there it moves. Now, if I create a second pair, so I flip another magnet over here, and I create another pair of these monopoles. Remember, there's like a north one and a south one, and we can think of them as a monopole and an anti-monopole. It's antiparticle. And we can create another pair, and if we can get any north next to any south by flipping, here we've got, this is the north from one pair, and this is the south from the other pair. If we flip the magnet between them, we get rid of them again. So this is the sense in which they're like a particle and an antiparticle. If you take an electron and its antiparticle, which is called the positron, it's the same as it in every way, but it has the opposite charge, electric charge in that case. Then if you bring a particle and its antiparticle together, they annihilate, they disappear, or rather they turn into a pair of photons, energy. And that's the same that happens with these magnetic monopoles in this story here. If you get any any north monopole next to any south, you can flip the magnet between them and they disappear. So what we should think of here is when there's two norths in and two souths in to a particular vertex where they meet, then that's like the vacuum of space. There's nothing there. When there's three norths and one south, that's like a north particle, a north charged particle, a magnetic monopole. And when there's three souths and one north, that's like a south particle, or the anti-monopole. So this story is very nice, but I've told it to you about magnets that I'm imagining sort of putting on a table and flipping around. What we'd really like is for these things to come about naturally in real materials, in some kind of crystal, down on the atomic scale. And we'd like it to give us the most simple description of how that material behaves. And that's why they're useful, right? It's a nice story, this, and you can make this out of magnets, and you can see that it's true. But I think what we'd really want to make these things be much more like particles is that we want them to be a simple description of the behavior, like the physics of something. When we make a measurement, it can only be explained by proposing that the real behavior is captured by the movement of these magnetic particles. So let me move on to telling you about where it is we're going to look for them. So it's in particular crystals called spin ice. And it looks something like this. This is a picture of the crystal that's been grown. It was grown by the crystal grower in Oxford University. Prabhakaran is his name. Dharmalingam Prabhakaran. And he grew this crystal. He grows these things. So it looks like this. It's a crystal. What that means is that on the atomic scale, the atoms are in a regular structure. And again, I spoke about this idea at length in my previous talk. I won't dwell on it now, but the point is that the atoms appear in a regular periodic structure, a repeating structure. And in particular, when we look down on the atomic scale, the atoms are arranged something like this. Now, the tetrahedron is the sort of pyramid made up of 4 triangles. The tetrahedra aren't there on the atomic scale, of course. They're just there to help you picture how the atoms are arranged. The atoms are these little balls here. And in fact, these are magnetic ions. They again, they have an electric charge and they have a little magnetic field each. And there are actually other atoms here that are neutral and I'm not showing them. And are not magnetic, sorry, and I'm not showing them. So here are the relevant magnetic ions in this material of spin ice. The material, by the way, it's dysprosium titanate. It's a fairly complicated material. It doesn't exist naturally, as far as I know. I think it has to be grown by people like Prabhakar. Now, if we look on the atomic scale, we see the atoms here, and each of them has a little spin, a little magnetic field. Okay, just like before an unusual magnet. But because of the particularly strange crystal structure, the way the atoms are arranged, we find that each of these ions, let's call this an ion, that's its proper name, shares a tetrahedron with 3 others. So each of them lives on, in fact, the meeting point between 2 tetrahedra. And on each tetrahedron, there are 4 of these ions. And each of them points exactly either towards the center of the tetrahedron or exactly away from the center. So either the north points in or the south points in. So it's really like a 3-dimensional version of the 2-dimensional picture I was showing before. And just like before, you would imagine that when the magnetic fields, these spins, want to minimize their energy, the way they'll do it is to have 2 point in and 2 point out of each tetrahedron, because then you've got 2 norths together and 2 souths together. And since you have to have 4 things there, and you want north to point towards south, that's the best you can do. So that's what I've shown in this picture. I've shown a few of these arrangements of these ions where it would be in the lowest energy state. Now, to get things into low energy states, to get a crystal to be in a low energy state, you want to cool it down, because if something's hotter, it's got more energy. And you need to cool these things down to extremely low temperatures. In fact, this material, this dysprosium titanate, becomes a spin ice. It starts behaving like this at below 2 Kelvin. So that's 2 degrees centigrade above absolute 0. So it's extremely cold. In a sense, it's colder than the universe itself, because if you go off into the middle of space, away from stars and things, you might imagine it would be absolute 0. There's no source of energy there. But actually there is. There's the cosmic microwave background around you. And that gives the temperature to the universe, which is something like 2.7 Kelvin. So that's actually hotter than this. You need to cool it down colder than the universe itself. I can't do that. I'm a theoretical physicist, which means I'm very impractical. But I have experimental friends who can do this routinely. So they cool this crystal down, and this happens on the atomic scale. The magnetic fields arrange themselves 2 in, 2 out on each of these tetrahedra. But they haven't gone to absolute 0. There's still some energy in there. And the way energy appears is that some of these tetrahedra, if we flip this spin here, then we get this tetrahedron here now has 3 spins pointing out. So it has a net amount of south inside it. And here this has 3 norths pointing in, so that has a net amount of north inside it. And just like before, we can color them and say if we blur our eyes so that 2 in, 2 out averages out to nothing, it's like the vacuum of space, then 3 in, 1 out, or 3 out, 1 in, this looks like a source or sink of magnetic fields. It looks like a particle, a magnetic monopole. And so we can flip a spin and we create a particle-antiparticle pair out of the vacuum. And really, this is a small-scale description of what's going on. And now if we flip subsequent spins, we can move the north pole away from the south, just like we could with the line of magnets. And this is what we believe happens in these materials called spin ices. And we can flip them around, and you can see which ones I flipped because I've colored them yellow. And if we get any north pole next to any south pole, just like particles and antiparticles, we can flip the thing between them, make them disappear back to the vacuum, and they're gone again. Okay. So this theory as to what's happening inside these materials called spin ices was come up with by these authors here back in 2008. And it's a theoretical description that explains some of the experimental measurements on that material. But it wasn't the only explanation. And what people wanted, the phrase people always use is they'd like a smoking gun. They'd like some real firm evidence that this is what's happening in these materials and that nothing else could explain all those experiments. And that's what we've tried to contribute towards, and I'd like to tell you now in this next part. Now, before I get on to it, I'd just like to explain briefly. This is a picture of ice. You might have asked why this thing is called spin ice. So here's these materials, dysprosium titanate. It's got nothing really to do with ice. You might have thought it's because it's very cold, but actually it's much colder than you need to get ice. Ice you need to get to 0 degrees centigrade. This needs to get to about minus 271 degrees centigrade, so very cold. In fact, the reason it's called spin ice is by analogy to water ice. So remember the spin, the magnetic fields in this picture have arranged into this 2-in, 2-out structure on the atomic scale. And if you look at ice made of water, so here's a water molecule in the bottom right, H2O. And liquid water has lots of these floating around. But when you freeze water into ice, it becomes a crystal. The atoms arrange into a regular periodic structure. And so you can see that the oxygens, for example, the black balls, form a regular structure, which is again made of tetrahedron. Now, each of those oxygens has 2 hydrogens close to it because water is made of H2O molecules. And so it gets 2 close hydrogens and then 2 far away hydrogens. And the way it arranges is kind of random in this crystal. And so it's this 2-in, 2-out rule again, but this time for hydrogens rather than for these spins. So that's why it's called that. It's called spin ice because spins, little magnetic fields, arrange themselves similarly to how water molecules arrange in real ice. Okay, so I've told you the route we're going to take to look for these magnetic monopoles. We're going to look in materials called spin ices, and we're not going to look for elementary particles. We're going to look for emergent quasi-particles or emergent descriptions in materials. Let me say a few more words about that. So the things I told you at the start about Paul Dirac's theory and the fact that electric charge would be quantized, become in these multiples of the smallest amount if we had a magnetic monopole somewhere in the universe. These magnetic monopoles will not do that. These are emergent properties within a crystal. You would need an elementary particle for those things to happen, and that's not what we're looking for. So they are a different thing in that sense. But the thing that convinced me that they're really real, and they're as real as an elementary particle, is that these magnetic monopoles in spin ice, they're floating around, but they can only exist inside this crystal. But it turns out that if you try to measure the magnetic field outside the crystal, you get some detector of magnetic field in principle, and you put it somewhere near the surface. Then as one of these magnetic monopoles walks towards the detector, as it moves around randomly in the crystal, and it moves away again, you'll see your magnetic field change in such a way that it looks exactly the same as if you had an elementary magnetic monopole particle. If that were there in that same region of space, moving around in the same way, your magnetic field detector would detect exactly the same thing. And it's really quite a unique signature. So it's a very clear signature that would be a magnetic monopole. So in that sense, I think even though they only exist inside materials as these kind of emergent properties, I nevertheless think they are as real as elementary particles. So we're going to look in these spin ices for these things. Now, here's a picture of one of these spin ices. Now, I'd like to tell you now about the expedition looking for this these magnetic monopoles, the particular experiment that I had the good fortune to be involved with in my capacity as a theorist that was carried out by some very talented experimentalists. And that is to look for monopoles by noise. So in a sense, listen for monopoles rather than look for them. And I'll explain what I mean by that. Now, first, let me show you the experimentalists who carried out the work. So on the left here is Ritika Desad, and she was the lead experimentalist on the paper. So she built the detector and she carried out the measurements. And on the right is Frank Kirschner. She was the lead numericist on the paper. So she's an experimentalist, or she was an experimentalist in her own right. But in this experiment, she was doing numerical computer simulations. She'd written a computer program that could simulate the behavior of these materials on the smaller scales. And Ritika and Fran are the lead authors on the paper. So they did the real work on this paper. And so let me tell you a little bit about how the story came about. So, and I'll give you my kind of subjective take on it. I was a postdoc in Berkeley in California. So a postdoc is after you've got your PhD, you spend a few years doing research in different places. And I met Norm Yao, a friend of mine, who's now a professor in Harvard. And Norm is a very talented person. He's a theorist, an experimentalist, and a numericist all in one. And he'd built an experimental device called an NV magnetometer. And this is an incredibly sensitive detector of magnetic fields. And he asked me if I had any uses for something like that. And he said, this thing is so sensitive to magnetic fields, in principle, it can detect magnetic fields on the scale of something like 50 atoms. So it can really measure down on the atomic scale for magnetic fields. And I thought, well, maybe you could actually use it to detect one of these magnetic monopoles as it sort of wanders towards the detector and away, that story I was just telling you. And so Norm thought, maybe that sounds plausible. So we spoke to Amir Yacobi, who's a professor in Harvard, who's an expert on this NV magnetometry. And we spoke to Steve Blundell, who's a professor in Oxford, who's an expert on spin ices and then these magnetic monopoles, amongst many other things. Now, it turned out Steve was thinking about a very similar problem, and his PhD student was Fran Kirschen, who became the numericist on the project. So she was already writing these computer programs to simulate what would happen. And she went ahead and wrote that. We wrote an experimental proposal paper together where we said, in principle, if you could look for these magnetic monopoles. And Fran gave a talk at a conference, and in the audience was an experimentalist called Seamus Davis, who's now a professor in Oxford. He was at Cornell at the time. And he's also at the university, he's at Cork as well in Ireland, so he's split all over the place. And he saw Fran give a talk about this prediction for how to measure magnetic monopoles. And he spoke to his PhD student, who was Ritika Desad. And within a week, we had an email from Seamus saying that Ritika had built the experiment and had made the measurements, and she'd found the signatures of these magnetic monopoles that Fran had predicted. So this is a hugely fast timescale. Typically, you would expect years to go by before anyone would build the experiment, but Ritika used some very ingenious methods to make it. So let me tell you a little bit about these, the experiment and the theory that really Ritika and Fran saw through. So there they are. So it wasn't quite the original proposal we proposed. What they realized is they could modify a device that they'd already built a lot of. Now, here it is. So here's the spin ice crystal inside the machine, or the detector. It's very small. The crystal is probably like this size. So to give you some sense of scale. Well, there it is, in fact, 6 millimeters by 4 millimeters, very small. And what Ritika did is she wrapped a coil of wire around the spin ice sample. And then she connected it to this symbol up here. This is a symbol for what's called a superconducting quantum interference device, or a SQUID, which is a very sensitive detector of magnetic fields, magnetic flux in particular. Let me, oh yes, okay. I want to show you my picture of a squid. Where is it? Here we go. I'm gonna put a nice octopus on there. Remember, we're sticking with this sort of Victorian explorer theme. There's a squid. It's actually an octopus, but I like this picture I found online. All right, so there you go. It doesn't look like that. It's actually a detector of magnetic flux, but here's a nice symbol for it. Now, this story of wrapping a coil of wire around something to detect a magnetic field, you may remember from the start of the talk, and I've shown you here a little bit of Faraday's picture from that experiment he was doing back in the 19th century. Remember, he moved a magnet in a coil of wire, and he could detect an electric current set up in the coil. Now, it turns out that if you take Faraday's exact experiment, just as he did it back 150 years ago, and if an elementary particle, a magnetic monopole, were to pass through that coil, it would give a very unique signature in the current that gets set up. In fact, it would establish a current that would just sort of keep flowing. And so essentially all that ended up being done, all that Ritika did, was really building a Faraday coil to detect these magnetic monopoles. And now it's not detecting the elementary ones, it's detecting the emergent ones within the spin ice crystal. And so the idea is that as this monopole wanders through the coil, it sets up this current that you can detect then, and the squid can detect that, what passes through the coil. So it's really the same basic idea that Faraday proposed all that time ago, but built with this really cutting edge technology developed by Ritika. Okay, and this is how they did the detection. Now, I'm going to show you something slightly different now. So what is it they actually measured, and what was Fran's prediction numerically? Because it wasn't, the original proposal was to detect the magnetic field outside the sample and see as the monopole wanders near and then away, and you detect this clear signature. But it turns out that at the operating temperatures at which you can make these measurements, you don't just have like a single monopole wandering around inside the crystal. Well, you always have at least two, but you have many, many more than that. So by analogy, we might say that it's as if you'd predicted the existence of raindrops. And you said, okay, if you go and listen for a raindrop, it'll sound like this sort of little splish sound, okay? And then you go outside, it starts raining, and you say, okay, great, let's go and detect this raindrop I predicted. And you go to detect it using your method, which is to listen to the sound of a single drop. But of course, when it rains, you don't get a single drop. You get a big downpour, and it just sounds like shh. It just sounds like noise. And that's exactly what Fran predicted. She said, okay, you're not going to detect a single magnetic monopole, there's too many of them. So you won't get just the signal, you'll get noise. You'll get the sound of loads and loads of monopoles at the same time, by analogy. Now, usually you think of noise as a thing that messes up your signal, right? Signal is the thing you want, noise is the thing that disrupts it. But actually, there's a lot of information hidden in noise. And what Fran's prediction was that if you take any sort of normal magnet, by which I mean a paramagnet, and that is something that's not magnetic by itself, but if you put it in a magnetic field, it becomes magnetic, so as to agree with the field, align with the field. If you take any of those paramagnets, they're very common things, and you measure the magnetic field coming off it as a function of time, it'll be changing slightly, constantly, because it's at finite temperature. And if you take the set, you can describe that as a set of frequencies, the frequency at which it's the magnetization is changing. And you can describe that by analogy with a set of sounds. Okay, so it's an analogy, but it's a good one. It's sort of mathematically robust. You can say the set of frequencies at which the magnetic field is changing, so as it just changes as a function of time. You can turn those into literal sounds. Now, any of those paramagnets, the normal magnet, is described by what's called red noise. And I've got a little demonstration of this because I think it's easier to kind of hear it than it is for me to tell you about it. I'm going to try and play you some noise. I hope you can hear it because the Zoom tries to stop noise. It has noise suppression, so it's a little bit hard to hear, but I'll give it a go. So let me show you this. So this is a program that you can access freely online. You can go to this website here. Maybe you can freeze frame and have a look. A student of mine, Leon Zaporsky, wrote this program just for this talk, basically. And so if you've heard of a type of noise, it's probably white noise. Now let me play you 1 second of white noise. It's not very nice to listen to. I hope it's not cancelled. I don't know if you heard that. I hope so. Let me turn up my volume so it's a bit louder in any case. Okay, let's try that again. Here's 1 second of white noise. Okay, so it should have sounded like so that's a mix. It's called white noise by analogy to white light. If you take all different colors of light and you mix them together, you get white. And similarly, if you take all pure tones, sort of like all the different tones, and you play them all together at the same time, you'll get a sound that kind of sounds like white noise. Now, a paramagnet, if you do this process of measuring the magnetic field and you can convert it into a sound, sounds instead like this. So let me, sorry, zoom slightly in my way. There we go. Okay, so that's blue. Let's go down to red. So red noise, by analogy, if you took all the colors of light again, but you took more of the redder colors, so the longer wavelength colors, then you would have it would be more red than white. You would have a bias in your mix of colors. And so this, you can do that with sound as well. You can take more of the lower frequency sounds, the longer wavelength sounds, and it'll, instead of sounding like for white noise, it'll sound like for red. Okay, so here's 1 second of red noise. And let me play white again. So high pitched goes to low pitched. Now, Fran's prediction in her numerical simulation was that, so you take any paramagnet, a normal magnet, and it'll sound like this red noise. But she predicted that because of the monopoles and spin ice, it won't sound like red noise at all. It'll sound like pink noise, which is somewhere between white and red. So it's all pretty hard to hear, but you can play around with this. So white is like red is like, and she predicted that in spin ices you get somewhere between the two. And in fact, it would be pink, and the pinkness would change. It would become, I think, whiter as the temperature increased. So that was her prediction. And again, just to explain, so it's an analogy, this like literal noise of sound, rather than what you're really detecting, or the squid is detecting, is a magnetic field or a magnetic flux. But again, just as your ear is sensitive to a range of frequencies of sound, so the squid is sensitive to a range of frequencies of magnetic field. Okay, changing at certain, as it oscillates around, as it changes. And it turns out that the set of frequencies the squid can hear, or detect in a magnetic field, is something like a few hertz up to, I think, about 2.5 kilohertz. And the set of frequencies you can hear with your ear goes up to about 20 kilohertz. So actually the range of frequencies the squid detects in magnetic fields is contained within the range of frequencies of sound that you can hear. And what this means is you can take the signal that was detected in that sample by Ritika's experiment, and you can turn it into a literal sound, a noise that you can just listen to. And so Ritika did this. And I've got an audio file for you here. I do, again, hope you can hear it when I play it. It's not cancelled by noise reduction. But in the first 3 seconds of this, it's before the sample is put in. And so what you're hearing in the first 3 seconds is white noise. This is just totally random magnetic fields with nothing in the sample holder. And then in the second 3 seconds, she's inserted the spin ice crystal. And what's going to happen is it's going to go from white down to pink. And there's a precise technical sense, which you could kind of see on that previous screen, being shown here. I haven't really explained what's going on, but there's a technical sense in which we can understand these whites and pinks, and we can measure them. But the point is, we're going to listen to the literal sound of detecting these magnetic monopoles and spin ices for the first time, as measured by Ritika. So it's going to go from white to pink. And when it does, it's because of these magnetic monopoles. So let's have a listen to this. That was white to pink. Isn't that, I found that really exciting. I thought that was a very cool thing to do. So you're really hearing magnetic monopoles for the first time in those second 3 seconds. Okay, and let me just share a quick picture of, So I'm nearly finished with the main part of the talk. So this is Leon Zaporski. He was my former summer student, in fact, at the time, who made that program telling us about the colors of noise, and we'll give you a link to that later, just so you can play around with it. Okay. So here was the experiment again, and that's what Ritika measured and Fran had predicted, that spin ices kind of uniquely amongst magnets will show this pink noise rather than red noise. And that's what Ritika measured. Okay, so that was the expedition, to go and find these magnetic monopoles. They're emergent particles inside these materials rather than elementary particles, but you can detect them because they make this mysterious pink noise rather than red noise. And we enlisted the help of this giant squid along the way, or rather it was a rather tiny squid, in fact, this very sensitive detector of magnetic flux. So let me finish the talk by telling you about new frontiers. Where do we go from here? And in particular, so when I first put this talk together 3 years ago, I would just tell you about the applications of some of this stuff. I'm going to do that in a second. I'll tell you about why we should care about magnetic monopoles. But before I do, I'd like to give you a brief update on what's happened in the previous 3 years. I mean, many things have been detected and so on. But something that was lacking when we made our numerical predictions, and then we did the experiment, was kind of a theory as to why magnetic monopoles would create pink noise. And that theory has now been put forward. It's been proposed. It was published in the journal Science last year. And it's a really fascinating theory. So, I think I'm still sharing my screen, I think. Let me just confirm I'm showing you the right thing. So let's show talk, there we go. Okay, so why do magnetic monopoles and spin ices show this pink noise? And it's actually quite mysterious. I'm going to show you me talking for a few seconds. The thing is that this theory of noise, using noise as the signal itself, is actually, that's not something we came up with. It's actually a very old idea. And arguably, probably the oldest recorded evidence of this is from a Roman poet called Lucretius, who's writing in about 60 BC. And Lucretius observed that if you see sunlight shining through a window and you see it kind of coming through like a gap in the curtains, and you look, you can see dust dancing around in the sunlight. And he observed at the time that perhaps the dancing of this dust is because of the buffeting of it by air molecules in the air. And that's now what we think. And the kind of mathematical theory of this was worked out by Albert Einstein in 1905. So Einstein explained the motion of a pollen particle in water. If you ever see pollen in water, you'll see it sort of jiggles around in a noticeable way. And it turns out that the motion of that pollen particle is described by red noise. It's that same red noise that you get from a typical paramagnet, normal magnet. And so Einstein explained the theory of red noise, and it's really because at each instant the pollen particle is being hit randomly by water molecules, and its direction changes totally randomly. So the direction of the molecules at any instant is random, and so that is actually a form of white noise, sort of like shh, if you turn it into a sound. And then the set of positions of the particle as it moves around, that's described by red noise. And subsequently, we've learned that loads of things are described by red noise and white noise. And they really follow the same mathematics that Einstein worked out. And paramagnets are one good example of that. But not much, that we have no decent mathematical theory to explain things with pink noise. Other things are known that show pink noise, but we don't know why pink noise comes about. Now, one place that we do understand where pink noise comes from is the idea of, so what Einstein was describing and what Lucretius saw before Einstein was what we now call a random walk. You can think of this pollen particle as it sort of moves around randomly. It's taking a random choice of direction to move in at each instant as it gets hit by water molecules. And so it does what we call a random walk. It walks around, but it does so randomly. But it's not, well, it is true randomness, but it's you can predict certain facts about it, like how far it'll get in a certain time, that sort of thing. And Einstein did that very nicely. Now, the theory of pink noise, or one of the ways we can explain it, is if you're hopping around, so the pollen is moving around on the surface of water, so that's like in a two-dimensional space. It can move in up and down or left and right, and that's it. If you are moving around so if you move around in any number of dimensions, if it's along a line or on a two-dimensional plane or three-dimensional space, you get red noise as you take this random walk. The only way to get pink noise is if you hop around in some place that doesn't exist with an integer number of dimensions, as a fractal number of dimensions. So somewhere between 2 and 3, for example. Now, what could something like that possibly look like? Let me show you a picture now. So if we take a triangle, this is a classic example of a fractal. Sorry, a triangle is not a classic example of a fractal. Triangle's a triangle. We get zoomed in, right? But if we take that triangle and we delete the middle bit, so we take a triangle out of the middle, then we get 3 triangles. And now we take the middle out of each of those triangles, we get some more triangles. And we do the same again and again. I think I've got one more for you. Have I got another one? I have. If I do this an infinite number of times, I keep taking triangles out, then actually there's still something left at the end. And that thing is what's called a fractal. Now, if you imagine you're like an ant trying to walk around on this picture. If the ant wants to walk around in the black region, that's fine. It can walk wherever it likes. But if it tries to walk around only on white, then it can still walk around, but it's heavily constrained as to where it can walk. It can't walk around everywhere on the plane. So it can't walk around in 2 dimensions. But it's also not walking around just on a straight line. So it's not in 1 dimension either. It's somewhere between 1 and 2. And if it walks randomly it makes random choices to which direction to take at each point, consistent with the set of places it can go, it turns out its movement is described by pink noise. So what's this got to do with magnetic monopoles? Well, this is the theory that's been come up with recently. I'm just going to give you the 2-dimensional picture because it's a bit easier to show. So remember, in that story, we said we want to arrange our magnets. There's 2 pointing in and 2 pointing out at each of the meeting points. And where we have 3 in, 1 out, or 3 out, 1 in, that's a magnetic monopole and an anti-monopole. Now, I said they can hop around, and that's true. Can hop them like this, for example. Let's hop it back to where it was. Now, if I try to hop in the vertical direction instead, by flipping this magnet, you'll see that what happens is it doesn't actually hop. What happens is I get 4 norths in and 3 souths in here. So actually, instead of hopping, it creates a second magnetic monopole pair. So there's 2 magnetic monopoles set in the same place here, and now there's 2 souths. And that would cost us a lot of energy to have 2 particles of the same magnetic charge sat on top of each other. So what we can say is that at low energies, that's just not allowed. That magnet can't flip because to do it would cost us so much energy. So we might as well, and if we look at the places we can get to, there are various magnets that can't flip for the same reason as we try and move around here. And so if those magnets can't flip, let's just take them out of the problem and say, well, they're not, it's as if they're not really there. The particle can't go in those directions. And so the monopole doesn't actually see the sort of two-dimensional space that I was showing you. It sees a subset of those places. It sees this kind of thing that's somewhere between 1 and 2 dimensions. And so that's one of these fractals. And that's the theory now that's been put forward as to why magnetic monopoles and spin ices show this pink noise, because they see a world that isn't exactly three-dimensional like ours. It lives in somewhere between 2 and 3 dimensions. Now, the precise name for this type of fractal is something called a percolation cluster. And in fact, it's the oldest fractal that was known. Most of our discoveries on fractals was really done in the 1970s when we got computers that could create pictures like I showed you before. But actually, the earliest fractals that were known of were discovered by a scientist, and a rather famous scientist, but someone who's not famous at all for the fractals, but actually she developed them, or she understood the earliest bits of physics to do with them. So the scientist in particular is Rosalind Franklin here, who I'm sure many of you have heard of. She's, of course, much more famous for this picture that she took, using X-ray diffraction to discover the nature of DNA. Is a hugely famous discovery, one of the most important discoveries in science. And Franklin came up she carried out the measurements and did a lot of the analysis there. But actually, before her work on DNA, she worked on coal. Back in the Second World War, she was studying coal, and in particular, how liquids and gases filter through coal. In fact, it was part of the war effort. She wanted to understand how to make better gas masks. And so if you take coal and you filter gas through it, perhaps you can filter out the bad bits so people can breathe properly. And in that discovery, Rosalind Franklin discovered the idea of the percolation cluster. She modeled coal as having, you can sort of say this, here's some matter. Now we randomly take bits out. And if we take enough bits out, then stuff can filter through, like water, say, can filter through the coal, or gas can get through the coal. If you don't take enough bits out, it won't get through. And exactly at the point where the stuff starts getting through, you get this fractal structure. And it's very similar to the one I was showing you for the spin ices. So the percolation cluster was come up with in the 1940s by Rosalind Franklin. In fact, she described herself as an expert on the holes in coal, even though she was much more better known for the DNA discovery. So that's the recent update I wanted to tell you, that we've now got a theory as to why magnetic monopoles and spin ices make this pink noise rather than red, where all paramagnets made red. And let me just finish up briefly. I think I've probably run out of time, but I wanted to give you a couple of applications of these magnetic monopoles and how we found them. Now, there's a few. Now, here's a picture of, here are these two-dimensional magnets again. Now, here's a real experiment that's been made back in 2018, where they've made magnets on the scale of about a micrometer. Now, these things can flip, just like I said. They point in these directions, but which direction is north and which is south can flip. And this is very cool. And it's they've shown that you can actually build computers out of this by moving the magnetic monopoles around in this. You can carry out computations. Now, one reason you might want to do this is that we're coming to the end of what's called Moore's law. So for the last more than 50 years, the density of transistors on computer chips has been doubling approximately every 2 years. It's exponential growth, and it underwrites large parts of the economy. We assume this growth is going to keep happening. It's not clear what's going to happen now that it's coming to an end. Of course, we're hitting up against physical limits, and Moore's law has basically ended very recently. So we need some kind of new technology to carry on if we want to keep increasing the density of computer processes. And this is potentially one sort of route that we might take. So this is a different way of doing computation. And in fact, the reason this is exciting is that it's been shown in these papers that you can carry out computation incredibly efficiently. So you may not think about it too much, but your computer gets hot, your laptop gets hot when you use it, and that has to happen. So there's a law of physics that says you have to create that heat. And in fact, there's just inefficiencies in computers that cause it to happen. But in principle, doing calculations using magnetic monopoles in kind of artificial ones like this, these are called artificial spin ices, you can do it much more efficiently. And that gives you energy savings, that saves you money, but it's also good for the environment because a huge amount of energy is used each year in carrying out computer processes. When I first gave this talk a few years ago, the statistic was that the data centers of the world used 40% more energy the year before than the entire United Kingdom. And I'm sure that that's only increased massively since then. So it's a huge amount of energy we're using constantly to do computer processes. If we can do them more efficiently, there's better for the environment. And one other application is let me make myself appear again. So with all these kind of theoretical advances, the technology we use to try and search for these theories ends up filtering out into everyday life and being practical. And this is a good example of that. So one example where the technology used to look for magnetic monopoles might turn out to be useful is in MRI scanning in hospitals. So basically every hospital has an MRI scanner, and it's sort of a big tube you get put into, and it's kind of a horrible process. This is loud banging noise, and what's happening there is that there's a huge magnetic field that's being applied to you, and it's used to detect the locations of water in the body. And the way it does this is the magnetic field couples to the spin, the magnetic field of individual protons inside hydrogen atoms, inside water molecules. And the reason you have to go into this big tube, it costs a lot to run and so on, these expensive devices, is because you need a huge magnetic field because the coupling to that nuclear spin is very small. So an alternative to this is if you could use a much smaller magnetic field, more easily achievable, if you could have a very sensitive detector of magnetic fields. But the detection device that Ritika built to look for these magnetic monopoles, at the time she made it, was the most sensitive detector of magnetic flux ever built. So there's actually already a paper showing, an experimental paper showing a proof of principle that you can make MRI scanners that run under much smaller magnetic fields if you use very sensitive detectors of magnetic flux. And so the technology Ritika built could one day end up having applications like that. And more broadly, I'd say the picture I showed you of the computer there, the artificial spin ice, feeds into this other idea of that we might get around the current implementation of electronics, which uses the charge of electrons. You know, that's electricity. That's how we do computers and logic and all that stuff at the moment. We can take that in new directions if we try and use the spin of an electron instead, so the magnetic field. And that's a whole area that's called spintronics instead of electronics. And perhaps spin ices could play a role in that. You can build kind of magnetic versions of electronic components. Okay, so I'm going to end there because I think I've yes, okay, but good. Sorry, I was just reading the messages suddenly, and it says you're not sharing the sound of the presentation. I hope you heard this entire thing, but I'm sure you did. So I'm going to end there because I think I've run out of time. But thank you very much for listening, and I'm very happy to take any questions you have.
Okay. Do you want me to pass the questions in the chat or to read them to you?
Oh, yes. Let me see. I can't see the questions in the chat, so yeah, if you could read them to me, that would be brilliant. Thank you.
Okay, so okay, I'm not sure if you're reading them in the chat, but
Oh, I am seeing them. Thank you. You pasted it. Yes, I see. So you said, so does the new developments in particle physics open up the way to get new particles and not only two in the nature? Okay, so let me try and understand that. So new developments in particle physics. Okay, so the way I would interpret that is we have the set of particles that we know of, and that's what we call the standard model of particle physics. And that would include things like electrons and the photon I mentioned before. And then there are theories of other particles that might exist that we haven't seen yet. And those would be called beyond the standard model. So then the question, as I understand it, is are there new developments that might lead to us discovering these new particles that we don't currently know about? Well, possibly. CERN has run at quite high energies now, so if you want to look for new particles, what we do anyway, is we can take existing particles and we can smash them together with lots of energy. And the idea is that Einstein's other famous result, E equals mc squared, says that energy and mass are really two sides of the same coin, just like electricity and magnetism are. And so if you smash things together with enough energy, you can create new mass and you can create new particles out of that. So I should have said that one of the ongoing experiments in CERN is to try and create magnetic monopoles. There's one experiment where we just look for them. Maybe they just exist naturally and one might just one day fly through our detector. And the experiments I talked to you about earlier, another use of those is that it lets us test that technology, because of course you build a detector for to detect some new particle, but how do you know if it's worked? Because if the detector wasn't working and you don't know if the particle is really there or not. So a use of these emergent magnetic monopoles is you can actually test your magnetic monopole detectors that are used for elementary particles. It does the same thing. So that's a link to what I was saying, and so then yes, perhaps we'll see them in CERN. We've tried hitting stuff together at very high energies to see if we can create new particles, and magnetic monopoles could well be those particles. So that the magnetic monopoles would be exactly something that's beyond the current standard model, but something that we might one day detect. And I would also add that as a condensed matter physicist, we get all sorts of particles that can exist inside materials that can't exist as elementary particles, that I try to argue are no less real. And magnetic monopoles are an example of this. That we don't know of them as elementary particles, but we can detect them and create them within materials. Okay, let's have a look at the other questions. So why is there only two kinds of charge in nature? Well, there's not actually. That's a very good question. Okay, good. So there's electric charge, positive and negative, and we'd like to think there's magnetic charge. We've never detected it, but if there was, that would be what's carried by magnetic monopoles. But actually, there are other charges as well. So there are different forces. I think that's the key here. So all of the stuff I've talked about is electromagnetism, and there's electric charge. It might be a magnetic charge, maybe. But there are other forces in nature as well. There's the strong and weak nuclear forces, and then there's gravity. In a sense, you can think of mass as like a gravitational charge, right? It's something that creates gravitational fields, just like an electric charge creates an electric field. So in a sense, you can think of mass as like a charge, a different sort of charge. And we have other strong and weak nuclear force. They have their own corresponding charges. We don't detect those on an everyday scale, but we can detect them in CERN. And then we have these other theories as what we might detect in materials, and then we would have equivalents to different forces and different charges coming about as a combination of other things in these materials in certain very special materials. So there are actually more than two, and it's similar to the particles question. We'd like to think that we're going to detect more in the future. So that's a great question. Thank you. Okay, so here's another question. Could magnetic monopoles be in the realm of dark matter? So we could macroscopically see matter behave like magnetic monopoles, although in the microscopic scale it is not possible. If it needs to be cooled down to such temperatures, it means it... Oh, sorry, these are lots of questions in a row, sorry. Okay, let me take them one after the other. So could magnetic monopoles be in the realm of dark matter? Good question. I'm not an expert. I think the answer is probably no there, because if you have a magnetic charge, then it does interact with electromagnetism. And dark matter, by definition, is dark in the sense of like light isn't interacting with it. And so light is the particle that conveys electromagnetism. So I think actually probably it would have to have an effect that you could see as electromagnetic radiation. I'm kind of doing this off the top of my head, but so I think probably not. But then again, maybe, because who knows? One theory of dark matter is that it's some new kind of particle that we haven't seen, like an axion, for example, and then that does fit in. Okay, that's something I can tell you about. So I'm going to reverse my decision. I like to try and say yes to things when people ask. And I think I've got a way to say yes there. So could it have something to do with dark matter? Maybe, because I think one of the leading contenders for dark matter is a particle called an axion. Again, beyond the standard model, we've not seen it yet. But actually, when you look for these magnetic monopoles in spin ices, well, not quite in spin ices, but if you take other materials, it's believed that these particles become quantum. So the story I told you is really classical, even though it's on the atomic scale. There's nothing particularly quantum in my story. But it's believed, and there's a big search on for materials called quantum spin ices, where these things start behaving in a quantum mechanical way. And then they're described very naturally as something very similar to an axion. So then you get something emergent in a material that would be like an axion, and an axion is precisely what you're looking for in dark matter. So in that sense, yes, perhaps they could be related. Okay, so then the other question was, so we could macroscopically see matter behave like magnetic monopoles, although in the microscopic scale it is not possible. Yes, that's a very good way to think of it. I mean, I wouldn't say these are macroscopic, right? Because the spins are really the spins of individual ions. So you have a magnetic monopole on the scale of like 4 ions. So it's not macroscopic means sort of everyday scale. But again, like your question is a good one, and if you have magnetic charge on a small scale, then in principle you can build it up on a big scale, right? In the same way you have electrons with their tiny electric charge, but you can rub a balloon on yourself and you get so much electric charge you can detect it with your hair. In principle, if you had magnetic monopoles, you could build up magnetic charge in that same way. And if you take one of these spin ice materials and you apply a big magnetic field to it, then you magnetize the sample. You send all the north poles to one end and all the south poles to the other, and it builds up a magnetic field across it. So that's like a magnetic, a macroscopic field, just as you asked about. So yes. Okay, so let's see. If it needs to be cooled down to such temperatures, it means it oh, sorry, it just jumped. It means it doesn't exist naturally. That's not okay, sort of. In a sense, yes, because the spin ice materials don't exist naturally. As far as we know, you have to make them. You have to have a very clever crystal grower like Prabhakaran who can grow these things when they don't exist naturally. So in that sense, you might say it doesn't exist naturally. On the other hand, once Prabhakaran grows that crystal, they do come about naturally if you cool them down enough. So I would say that kind of, it sort of is natural. It's not like you're having to manipulate the thing to create the magnetic monopoles. They come about naturally of their own accord if you cool them down enough. Now that's true of a lot of interesting states of matter, right? I'd still call them natural. It sort of depends where you go. Now, high energy things like lots of processes that happen in the sun, for example, that don't happen on Earth, they're still natural. But I take your point that if you have to cool it down to colder than the universe itself and the crystal doesn't exist, then in a sense it's kind of unnatural. I suppose the universe is cooling, so you know, in the far future it'll cool down enough for this to actually come about naturally if the material happens to exist. But yeah, in a sense it's kind of unnatural. But I think it's natural enough for me to be happy, at least. I hope it's perhaps you think of it the same way. Okay, would it be possible to put coils around the globe to detect this monopoles? They don't need to go around the globe. You know, we can do them locally, and that's actually exactly one of the detectors that's going on that's been looking for these monopoles. So you really do just build a Faraday coil again. You build a coil of wire, and you wait for a monopole to shoot through it, and it has this very distinctive signature in the current that it sets up. And that's one of the experiments that's been going on since the 1980s. As I mentioned at some point, there's something called the Valentine's Day monopole. There was this detector gave off a signal that said I detected a monopole on Valentine's Day in I think 1982, but it's never gone off again. And there, you know, possibly there are other like errors that could have caused that. So I think generally we think it probably wasn't a magnetic monopole. But anyway, so it doesn't have to go around the globe. But yes, you build these coils and you can detect it. And there was a follow-up that said in different latitudes and longitudes. I mean, it would work, your proposal would work, but you'd need a lot of funding to build a giant Faraday coil like that. And you don't need it to go around, you know, I hope I didn't cause any confusion with my globe picture and so on, but I was giving a sort of just a theme to the talk when I was talking about moving around on the Earth. We're looking just at these tiny particles. But yes, you could build a big detector out of Faraday coils and see one pass through. And we're doing that, but they don't have to be that big. Thank you for your answer. Do you think in the breaking of symmetries in the Big Bang, monopoles were broken or sort of, and that is why to see them we need specific conditions now? Well, that's a very nice question. Yeah, I mean, that's basically one of the main theories as to how they might have come about. And also that would be a very natural explanation as to why you might only expect to see like one magnetic monopole in the observable universe. that sounds like a sort of strange suggestion, right? Because how many electrons are there in the universe? Many, right? I think there's something like 10 to the power of 80 particles or something in the universe. So you wouldn't, if there's a new type of particle, you wouldn't expect there to be one in the universe. You'd expect there to be loads, naturally. So then why haven't we seen them? Well, it might just be that they're very heavy. If they're heavy enough, we wouldn't have made them in CERN, and they might be so heavy you're never going to make them in CERN. But there's a very nice theory that says, well, they might be what's called a topological defect in the universe. Let's see, how can I explain that? Well, okay. I mean, the basic idea is that so when the universe expanded under inflation, parts of it became inaccessible to other parts. So, you know, the analogy we like to give is, you imagine you're on the surface of a balloon walking around, and then the balloon starts inflating. Then if it inflates fast enough, then light can never reach from one point to where you are, and you'll eventually sort of see less and less of the universe. Okay, so in that process, it turns out that the universe can sort of break into different parts, and at the breaking points, you can get particles. This is one way to think of it. Magnetic monopoles are one example of that. Cosmic strings would be another example. They would be like a long string of these things. So yes, in that sense, yes, if magnetic monopoles exist as elementary particles, then I'd say one of the leading theories is that they came about naturally as the universe expanded, and yeah, that would be what we think of it. And that is why, to see them, we need specific conditions now. Yeah, I mean, then if that theory is correct, then there'd just be very few of them in the universe. So I'm not sure how we go about detecting them. We'd have to come up with some very clever methods of looking for them in the night sky or something in that sense. But yeah, so yeah, very good point. What developments could arise from the existence of magnetic monopoles? Let's see. I guess it depends if we're talking about elementary particles or emergent magnetic monopoles in spin ices. Let me think about that. Yeah, so I don't know which one to answer. If I can get a follow-up, I can answer more precisely. In the meantime, I can say, in terms of the applications I gave at the end, development that would arise from the existence of those emergent magnetic monopoles would be the sorts of things I was trying to mention there. So, for example, you can get like a magnetic version of electricity with magnetic monopoles. So electricity and magnetism, of course, both play a big part in our lives. Oh yeah, in everyday electronics or quantum computers. Good, exactly. So that's the thing I was trying to answer with. So both electricity and magnetism are hugely important in our daily lives, right? But maybe we use electricity a bit more. Like, you're watching this mostly because of electricity, I'd say. Okay, magnetism is used still a bit in some computers for hard disks. It's kind of outdated now. But why is it that electricity seems to be more important than magnetism to us when the two should be sort of equivalent? Well, it's exactly that one thing that's not equivalent that makes them different on that point. And that is, if I want electricity, I can just go to the plug socket and turn it on, and I get electricity out of the socket, right? It's like turning on a tap with electricity. But I can't do that with magnetism. I can't have a current of magnetism, because when I get a north pole, I get a south pole along with it. So when I want to send an electric current down a wire, it can be conveyed by like electrons or what have you. Just positive, a particle that has an electric charge, a flow of many of those particles gives me an electric current. But I don't have a particle with magnetic charge, so I can't make magnetic currents either. Or at least I can't have like DC ones, direct currents. So I can't turn on the tap and get magnetism out. And in that sense, electricity is a bit more useful. But with spin ices, you can make magnetic versions of electrical things. So we could have what you might call magnetronics, which were like electronics, but with magnetism. We already have spintronics, and actually they're already like spintronic computer devices that are being made. You can buy yourself a spintronic hard drive, I think. It's very expensive, but they exist. And I think that's probably something you're going to see a lot more of in the near future, is spintronics. Magnetronics is, in principle, something else you can do. So you can take any electronic components you want and make a magnetic version of them now. Again, actually, they have to rely on, they only work with AC currents rather than DC, but that restriction aside, then you could make them. So I'd say that's one of the main reasons these things might be quite exciting. You might say, well, I have to cool it down to 2 Kelvin. I'm not going to do that in my computer, but we use cloud computing these days, quantum computers that people are building only work at very low temperatures in the same way. So you're going to, you're only going to access quantum computers probably via the cloud and that kind of thing, right? You're not going to have the physical quantum computer in your house. So you could say, well, I'm imagining here, but if we try to use spin ices for these magnetronic applications, it would be sort of cloud computing type thing. Is the titanate material you mentioned the only one used to detect monopoles? Okay, yeah, that's good. So there are two spin ices. There's dysprosium titanate and there's holmium titanate. And both of those have these monopoles. More recently, actually, there have been a few other materials that seem to show these monopoles. There were, let's see, I think gadolinium titanate. There are a few others like the titanates, but actually there's been different families of materials discovered that aren't of that general form now. So there's a few different ones, but it's a limited set. But I suppose there's a broader picture. There's a whole set of things that are kind of like magnetic monopoles in different materials. They have all sorts of fascinating features and are used for things like, they might give approaches to quantum computing, for example, where we can carry out quantum computation by creating these weird particles and moving them around each other in certain ways. So they're not magnetic monopoles in quite the same way. Like these magnetic monopoles I talked to you about really have all the signatures of an elementary magnetic monopole, all the stuff you'd want to look for. There are this broader class of things that are a bit like monopoles. They have all sorts of weird properties. So just to give, since I imagine a lot of people listening are interested in elementary particle physics, you have all particles divided into two classes. There's bosons and fermions, you may have heard of. And those are the only two options. But in materials, if you have layered materials, they're very thin, you can get a third option. And these are called anyons. And they're really bizarre things. In a sense, they have a sort of memory of where they've been before. It's a very odd situation. And we've detected these things now. We've got kind of fairly recently confirmed the existence of this third fundamental class of particle in materials called anyons. And certain types of anyons are what we would use to make a quantum computer. It's called a topological quantum computer. A special kind that would be is one potential practical route to building a useful quantum computer. So there are other things like this. They're not quite magnetic monopoles, but they're kind of similar. So and those would be there's plenty of other materials. Some of them are material independent. So those anyons, you take a sort of thin sheet of materials and put a magnetic field through it, but it's not really a material property. It's more a property of these layered materials under the right conditions. Okay, so I think I've got two. Oh, here's another question. So quite interesting, but I have taken a lot of your time. One last question from LinkedIn feed. We are streaming from Twitter, YouTube, Instagram, Facebook. We have enjoyed the seminar a lot. Thank you for your time. Thank you very much. That's lovely to hear. When the magnetic monopoles are found, Maxwell equations will be symmetric. How would our understanding of the electromagnetic interactions be changed or completed? Oh, that's an excellent and quite technical question there. You've reminded me I should have pointed out, of course. So Maxwell's equations were the lists I was referring to earlier when I said write down a list of all the stuff in magnetism and all the stuff in electricity, and we see there they exactly correspond. The list is really the list of Maxwell's equations, and you find there's four of these, and one of them says electric charges exist and magnetic charges don't, and that's the only one that disagrees. So I should say that finding these these emergent magnetic monopoles and spin ices doesn't require us to rewrite Maxwell's equations. Again, because they're kind of emergent properties. But if we did find elementary magnetic monopoles, so elementary particles, then yes, we would update Maxwell's equations. That one where there's a discrepancy, we'd update it so there's no longer a discrepancy. And the laws of electricity and magnetism would then be perfectly in correspondence. And that's one of the reasons physicists think these things should exist, because when we see a massive list of two things and they agree on every entry except for one, you tend to think there's an error in that entry. I mean, I should say, so the question is, if we find elementary magnetic monopoles, I think, how Maxwell's equations will become symmetric, how would our understanding of the electromagnetic interactions be changed or completed? Well, we'd have to update the list, but then the consequences of that would be those that Dirac pointed out all the way back in 1931. Well, no, okay, let me, since you've asked a technical question, I'll give a slightly more technical answer. There are kind of two options. One is that Maxwell's equations stay basically unchanged. We don't update what we've seen, then, and that's what Dirac was talking about, I think. So his charge quantization argument came about from saying, let's say that Maxwell's equations have to stay intact, but magnetic monopoles exist. There's this condition that ends up with charge quantization, which allows those two things to exist in a compatible way. Or at least you send your monopoles off so you haven't detected them. They would cause okay, that's too technical. The other option is just that we update the laws of the Maxwell's equations and just say there is a magnetic charge now. In both cases, we've worked out the consequences of those things. The laws of nature would be much sort of neater and more beautiful in a sense if magnetic charges did exist. And I think that's really like the basis of things like string theory is, that things, so that really it's grand unified theories require the existence of magnetic monopoles. And people thought they'd found a way to get charge quantization without monopoles, but then they found that monopoles existed in these theories anyway. And that was kind of rather suspicious that led us to think that maybe these things do exist. We thought, oh, there's many ways to get charge quantization, but it turns out that all the other ways we thought we'd come up with in one way or another actually contained magnetic monopoles in the theory secretly. So they're always kind of there. And so since we do have charge quantization, that's kind of, in my mind, a good argument that these things probably do exist. Anyway, I hope that kind of answered the question a little bit. Beautiful explanation, thank you. Elegant and simple. The last question from Twitter, could monopoles exist in multiple dimensions, like in string theory? Yeah, I mean, there's a big connection between those two things. Yes, yeah. Can I give any specific? Well, I mean, okay. So I think string theory does require magnetic monopoles. So in that sense, yes, it also requires multiple dimensions. What more do I want to say about it? I'm currently very excited about a particular type of thing that's almost a particle. It's called an instanton. These are very weird things. And I'm working on those at the moment from both the kind of condensed matter side, but also particle physics side. And depending on which dimension you're in, sometimes instantons are magnetic monopoles, and in other dimensions they're not, but they are things that have similar sorts of properties. There's a whole theory of instantons if you want to look it up. They're very fascinating things, but there's a deep connection to the number of dimensions in which you live and the types of structures that you get from these things. And they're very closely linked to magnetic monopoles. So that might be the direction to look in if you want to look this stuff up a bit more and find some stuff on monopoles and extra dimensions. That might be one way to go, looking up instantons, or there may be just things that are on my mind right now. But thanks for the question. I've dodged it a bit, but my hope here is really to inspire you to read more about this stuff, right? I'd love it if you all take up a further study of this subject. Okay, and then any final thoughts? I don't think so. I mean, it's 11:43 p.m. Here in England. I think I'm a bit beyond final thoughts at this point, but thank you for your time. I'm happy to answer any questions people have by email. If people want to contact me, you can email flicker@physics.org. So please take a look there. I suppose there's one thing I'd like to mention finally. If you go on my website, felixflicker.com, my publications are there. I actually wrote up an article for Science about the recent fractal story that I told you at the end there. And that's a popular science description, so you can take a little look at that. All my papers are free on there, but that's a paper you can access, which is kind of written for an accessible audience. I've also written a book which covers this whole topic in one of the chapters. That's the magic of physics is how it's published in North America. So feel free to take a look at that book, and I'm happy to answer questions as well. So thank you again very much for your time and for having me.
No, thank you, Professor Flicker, for your time and for this interesting exposition. I will apologize because of how late we keep you, but it was certainly very interesting and, as someone said, beautiful, simple, and elegant. And we hope to have you here on the Lederman seminar series sometime in the year. And you are always welcome to participate with us in all the activities of the STEAM program. So on behalf of the director of the Elementary Particle Laboratory, Dr. Julian Felix, we wish to thank you for your time for this beautiful seminar. And we hope all the viewers can review it on the several social media that it's being streamed. And see you next time with the next seminar, which is going to be Gauss and Ampere's law. Thank you very much, Professor Felix, and see you next time.